Cauchy's theorem is one of the most important theorems in all of continuum mechanics. It's a theorem that connects the concept of global linear and angular momentum balance to local versions of those laws that allow us to solve boundary value problems. And it also establishes the existence of the stress tensor, as we will see over the course of this lecture. So let's begin with the setup here. So you consider a body that's subjected to a force system, and we'll look at a part of the body, PT, and it's subjected to surface tractions T, which depend on position and the orientation of the surface N, and conventional body forces B naught, so forces per unit volume. So that's the setup. And linear and angular momentum balance tell us a couple of things. One is that the time rate of change of the linear momentum is supposed to be equal to the total force acting on the part of the body. And there should be two time derivatives here. So it's mass times acceleration. So let me just fix that up. So rho u double dot and rho u double dot. So the time rate of change of the linear momentum is equal to the total force acting on the body, and the time rate of change of the angular momentum is the total moment acting on the body. So the moments are generated by the body forces and the tractions which generate the forces. And these statements hold for all parts PT of the body BT. And what Cauchy's theorem tells us is that this holds if and only if there exists a tensor field sigma such that, one, that the traction field is equal to sigma acting on the normal vector, two, that this tensor field sigma is symmetric, so it's equal to its transpose, and three, that the divergence of this tensor field plus the body forces is equal to the mass density times the acceleration. So this is what Cauchy's theorem says. It establishes an equivalency between these global statements up here and these local statements, which are given in terms of a tensor field sigma. This first result here is known as Cauchy's law sometimes, so you may hear that as a synonym. The second result here is actually a consequence of angular momentum balance, slightly combined with linear momentum balance. And this third result here is a consequence of linear momentum balance. And really what we have here are local manifestations of the global statements of linear and angular momentum balance. And it's important to note that the statement is if and only if. So global linear and angular momentum balance imply these three results, and these three results also imply global linear and angular momentum balance. So this is the statement of Cauchy's theorem, and what I'm going to go through now is a proof of this theorem. And what I'm going to do is I'm going to prove the necessity of the theorem. So I'm going to prove it in the forward sense, assuming the global statements of linear and angular momentum balance hold, and prove the three local statements. The second part of the proof would involve the sufficiency part of the proof. That would start with the local statements and generate the global statements. That one is actually pretty easy to do once you've seen the forward part of the proof, because all the steps in the forward part of the proof are fully reversible. They are just algebraic and calculus steps. So you can just run them in reverse and prove the reverse part of the theorem. So to start the theorem proof, we're going to work with a construction here known as the pillbox construction. And so what we'll do is we'll look at a point little x, and we'll consider a little chunk of material that's a flat box. Side lengths are delta, and the thickness is alpha times delta. And so you want to think about delta and alpha being small numbers. The normal to the top of the box we'll call n, and the normal to the bottom of the box we'll call minus n. So if I now apply, so think of these as small, and if I now apply global linear momentum balance, because the dimensions are small, to do the integrals, I just multiply the integrand by the corresponding volume or area. So from the acceleration term, I'll have rho u double dot times the volume of the pillbox, which is alpha delta cubed. And from the body force, I'll get b naught times alpha delta cubed. And then I need to evaluate the surface integrals, and there are 4 sides to the box. So each side of the box has area alpha delta squared, and I need to multiply that by the traction vector on the side of the box, and that's going to be a function of the normal. So I'll just say that n side I, and I sum I equals 1 to 4 to go over the 4 sides. And lastly, I have the traction on the top surface times its area, so that's t evaluated on n delta squared, and then I have the traction on the bottom surface, so t evaluated on minus n times delta squared. So that gives me all the forces acting on the pillbox on the right hand side here, and we have the time rate of change of the linear momentum on the left side here. What I can do now is divide through by delta squared, so all the delta squared terms go away and the delta cubes turn into deltas. And now I can pass to the limit as delta and alpha go to 0. And if I do that, all the terms disappear except for the last 2 terms on the right-hand side there. So everything goes away except for these 2 terms, and they generate this result here, that the traction at this point that we're looking at, evaluated on the upward normal, is equal to the opposite of the traction when you evaluate it on the downward normal. So if I evaluate t on minus n, I get minus t acting on n. So this is a nice result. And really what this is it's just saying action equals reaction. So it's a form of Newton's third law, but we've actually proved it here from what is sometimes called the first law, the balance of linear momentum. Just drawing this out pictorially, we can consider our point little x and draw a surface through it. So here's my surface. And we can look at this surface here from 2 sides. So one side will have normal n, and the other side will have normal minus n. So it's like making a section cut through the point x. And what this result from the pillbox construction is telling us is that the traction vector acting on the side with normal n is really pointing in the equal and opposite direction as the traction vector on the opposite side of the section cut. So that's really the action and reaction aspect of this. So this is a result that we're going to want to use as we move forward on this. So let's continue, and what we're going to now do is another construction, which is known as the Cauchys tetrahedron construction. So what I'm going to consider is looking at a point little x, and I'm going to look at a tetrahedron material, and I'm going to label each, it's a regular tetrahedron, and the edges of the tetrahedron I'll label 1, 2, and 3, so we'll make them 90 degrees to each other. The normal to the slanted face of the tetrahedron we'll call n, and the area of the slanted face of the tetrahedron we'll call it a delta. And the reason for that is if I look at this tetrahedron from the side, I'm going to let delta be the distance from my point little x to the front face of the tetrahedron. And the other thing to note here is that the volume of the tetrahedron is going to be 1/3 a delta times delta. So that's just a fact of geometry there. And now what I'm going to do is the same thing that I did with the pillbox. I'm going to apply global linear momentum balance to this tetrahedron. I'm going to think of delta as small, and that will allow me to express the integrals in a very simple form, simply multiplying the integrand by the corresponding area or volume of the integral. So, global linear momentum balance involves a number of terms. Let's start here with the acceleration term. So I have rho u double dot times the volume. So that's the integral of rho u double dot. And then I have similarly for the body forces, b naught times 1/3 a delta delta. And then I have 4 terms for the tractions. So on the slanted face, I have the traction times the area, and it's evaluated on its normal, which is n. And then on the back face, whose outward normal is minus E1, I'll have T evaluated on minus E1 times the area of that back face. So that's this face back in here. And then I have on the face whose normal is minus E2, I'll have T minus E2 times A2. So that's the other part back here. And then I have the bottom part of the tetrahedron, T, whose normal acting on the normal minus E3, and times the area A3. So this is A3 down here. It's useful to note that A1 is equal to A delta times the dot product of the normal vector times E1. And in a similar fashion, A2 is A delta n dotted with E2. And A3 is A delta n dotted with E3. So that's kind of a convenient thing to notice. I can now divide through by A delta. So all the A deltas cancel. There's one in every term. And I can take the limit as delta goes to 0. So that's going to tell me that T evaluated on n is equal, or let me keep everything on the same side. So what I'm going to do now is I'm going to move this minus sign outside of each one of these terms here. So I'm going to use the fact that T of minus n is equal to minus T of n, which is what we proved with the pillbox construction. And so if I do that, then I get T acting on n is minus TE1 n1 minus TE2 n2 minus TE3 n3. So I can crunch those terms together, those last three terms, and I can move them to the right-hand side, and I can express them as T acting on EI, outer product EI, acting on N. So you can see now that the traction is actually a linear function of N, and that operation here that is mapping N to the traction is just simply a tensor. So I'm going to call that tensor sigma. And so I arrive now at the first part of Cauchy's theorem, which says that the traction T at a point x, whose orientation is n, is equal to sigma at that point times that vector n. So we've now succeeded in proving one part of Cauchy's theorem in the forward direction. Actually, we've succeeded in proving two parts. We've shown what sigma is, so we've shown that sigma exists and has a well-defined definition, and we have shown Cauchy's law here. Okay, so there are two more parts to show, so let's continue. So let's go ahead and now combine these results with the statement for global linear momentum balance. So we have the integral of the density times the acceleration is equal to the integral of the body force plus the integral over the surface of the tractions. So what I'm going to do now is I'm going to take this last term here and I'm going to substitute in for the traction. I'm going to substitute in this tensor field sigma acting on the normal n. And I will now apply the divergence theorem to that to show that that's equal to the integral over the part pt divergence of sigma. We can pull all of these terms over to the left-hand side, and then they will be equal to 0. And this statement needs to hold for all parts pt of the body bt. And so I can use the localization theorem, and that's going to tell me the divergence of sigma plus the body force is equal to the density times the acceleration. So that was the third part of Cauchy's theorem that we were trying to prove. And if I write this out additionally, it's sigma ij comma j, so that's divergence, plus b naught I is equal to rho u double dot I. And so this really is a statement of linear momentum balance, but it's the local form. Okay, so there's only one step left to prove, or part to prove of the theorem, and that is that this tensor sigma here is symmetric. So in other words, that sigma is equal to sigma transpose. So that's the last thing that we need to prove. So the way we're going to do that is we'll use global angular momentum balance. And I've written this all out in indicial notation. It's just a little bit easier to do the proof this way. So we have, in the first term, we have a cross product. So the permutation symbol Eijk is being used. So the cross product of the position vector with respect to rho times the acceleration. And then we have the cross product of the position vector with respect to the body force. And in the last term, we have the cross product of the position vector with the traction. And we're just going to simply use the results that we've derived so far to rewrite this and come to the final result. So we'll first start with the last term. We'll take the traction and we'll replace it by stress tensor acting on the normal. And then we'll use the divergence theorem to write this as an integral over pt. So we'll end up with Eijk xj sigma kl comma l. So this is just using the generalized form of the divergence theorem. And we can now pull all of the terms over to the right-hand side. So I'll pull, every term has an Eijk, so I'll pull that out. So we'll have the body force term here, xj b naught k. And then I need to take this derivative here, this comma L on this term. So I'll have a xj comma L. That's going to give me a delta JL. And the stress I just rewrite, that's sigma KL. And then I'll have xj sigma KL comma L. So that's that term there. And then the last term is the acceleration term is going to go over here. So if I look at the first, third, and fourth terms taken together, I can rewrite those as xj sigma kl comma l plus b naught k minus rho u double dot k. And we'll recognize that what's in the parentheses is what we just finished proving, namely that the divergence of the stress plus the body force is equal to the density times the acceleration. So what's in the parentheses there is equal to 0. And so that means that there's only one term remaining in this integrand, and that is Eijk sigma kl. So I use the properties of the Kronecker delta to get rid of the L. And this has to hold true for all parts pt of my body bt. So that tells me that Eijk sigma kl needs to be equal to 0. So just using the localization theorem. So this is the local form of angular momentum balance, though we've kind of merged some facts that come from linear momentum balance into this construction here. And what I want to do is show that this relationship implies that the stress needs to be symmetric. So what I'm going to do is I'm going to go ahead and I'm going to multiply through this relationship here. I'm going to multiply this by EI PQ. So that's just right there, and that still needs to be equal to 0. And then I'm going to use the relationship between permutation symbols and the Kronecker delta to rewrite EIPQ IJK as delta PJ delta QK minus delta PK delta QJ sigma KL. So that's just this guy here, and that's still equal to 0. And now what I can do is multiply out all these terms and use the properties of the Kronecker delta. That's going to tell me that sigma PQ minus sigma QP is equal to 0, which just simply tells me that the components of the stress tensor have to be symmetric. So I conclude then that sigma is equal to sigma transpose. And this then here is the local form of angular momentum balance. So that completes the forward proof of Cauchy's theorem. So if I just flip back here to what we had, so we were trying to prove Cauchy's law, the fact that it's symmetric, this tensor that appears here is symmetric, and that the divergence of this tensor field plus the body force is equal to the density times the acceleration. And so this gives the complete forward part of the proof, starting from global linear and angular momentum balance and improving these consequences. And the reverse part of the proof, going upwards, can be done by simply reversing all of the steps that I showed before. And that would complete the full proof. But the forward part of the proof is the one that's most instructive here.